life returned to one of the harshest landscapes on Earth in a way almost no one expected. Not through massive machines roaring across the desert, not through endless pipelines pushing water against gravity, and not through a dramatic technological breakthrough announced with headlines and applause. It came back quietly, almost invisibly, triggered by a small native bee that had lived in the Negev Desert all along, ignored, underestimated, and largely forgotten. This is not a miracle story, and it was never meant to be one. It is a system story, a lesson in how ecosystems actually function, and why even the most advanced engineering struggles when it treats nature as something to override instead of something to understand. The Negev Desert in southern Israel is an unforgiving environment by any scientific measure. Rainfall is scarce and unpredictable. Summer temperatures routinely push past human tolerance. At the surface, moisture evaporates within minutes. Soil is thin, rocky, and stripped of organic matter. These are conditions that defeat most forms of life, including many that humans attempt to introduce with money, machinery, and good intentions. Israel has spent decades confronting these constraints head-on. Tens of billions of dollars have been invested in desalination plants along the Mediterranean coast, national water carriers stretching hundreds of kilometers, and electrically powered irrigation systems that keep vegetation alive where nature alone would not. From an engineering standpoint, these systems are remarkable. They turn seawater into fresh water. They move it uphill across deserts. They make agriculture possible where it should not exist. But they share a fundamental weakness that every engineer recognizes. They only work while humans actively sustain them. Pumps must run continuously. Electricity must flow without interruption. Maintenance must never stop. The moment that chain breaks, vegetation collapses rapidly. Roots dry out. Soil hardens. Life retreats. The desert does not negotiate, and it does not wait. That reality exposes a deeper truth that technology alone cannot solve. Engineering can keep individual organisms alive, but it does not automatically create a self-sustaining ecosystem. Living systems are not static installations. They are networks of feedback loops. They require organisms that move nutrients, shape soil, regulate moisture, and enable regeneration without constant external input. Without those internal processes, green landscapes remain fragile overlays, dependent on permanent human effort. In the Negev, one of those internal processes has always existed in plain sight: the acacia tree. Long before pipelines, pumps, and irrigation grids, acacias anchored life across the desert. Species such as Acacia tortilis and Acacia radiana evolved to survive where almost nothing else can. Their roots penetrate deep underground, tapping moisture far below the sun-baked surface. They fix nitrogen, slowly enriching soils that would otherwise remain biologically poor. Wherever an acacia stands, insects gather beneath its canopy, birds nest in its branches, and mammals pass through to feed and rest. Each tree becomes a living island in a hostile sea of sand and stone. But even these trees, shaped by millennia of adaptation, have a critical vulnerability. They depend on a very narrow reproductive window. Acacia trees bloom briefly each year, sometimes for only a few days. If their flowers are not pollinated within that short period, no seeds form. Without seeds, there is no regeneration. Without regeneration, even the toughest survivors slowly disappear. Old trees die. No new ones replace them. Over decades, entire stands vanish quietly, without dramatic collapse. For years, this problem went largely unnoticed. Researchers planted saplings. Irrigation lines were extended. Young trees were protected from grazing animals. Acacias survived, but they did not spread. Natural regeneration remained weak and unreliable. That contradiction forced scientists to look closer at what was missing, not in terms of infrastructure, but in terms of biology. The answer turned out to be an organism few people had ever heard of. A small native solitary bee known as Enrina sinai. Unlike commercial honeybees, this species produces no honey. It does not live in colonies or hives. It cannot be transported, managed, or multiplied on command. Each female lives alone, nesting underground, emerging only briefly at dawn and dusk. Its life cycle is short. Its movements are subtle. Its presence is easy to miss. For decades, it was classified as ecologically insignificant outside of academic interest. When researchers suggested releasing millions of these bees into the open desert, skepticism was immediate and intense. Many experts believed the bees would die almost instantly. The heat was extreme. Surface moisture was nearly non-existent. Sandstorms could bury nests overnight. From a conventional engineering perspective, the proposal made little sense. Critics described it as naive, reckless, and doomed to fail. But the research team approached the challenge differently. Instead of trying to protect the bees from the desert, they focused on understanding how the bees had survived there historically. The desert was not the enemy. It was the context. No artificial water sources were introduced. No shade structures were erected. No attempt was made to control the bees themselves. Instead, the desert surface was subtly modified to alter micro-conditions in precise, limited ways. Dark basalt strips were placed strategically to absorb heat during the day and release it slowly at night, encouraging condensation. Soil composition near nesting zones was adjusted to improve shallow moisture retention without introducing foreign materials. Nesting areas were aligned with natural wind corridors that promoted early morning dew formation. The objective was not comfort or abundance. It was timing. Extend moisture availability by a few critical hours. Hours, not days. Small adjustments, not dramatic interventions. When approximately 2.4 million bees were released, early results appeared to confirm the critics' fears. More than 40% died within the first few weeks. Sandstorms erased surface signs of activity. Media coverage labeled the project a failure. From above, nothing seemed to change. Below ground, something else was happening. Sensors buried beneath the surface told a different story. In zones where bees survived and established nests, deeper soil layers were holding moisture far longer than expected. This occurred without irrigation, without added water, and without continued human input. The desert itself was behaving differently. To isolate the effect, researchers divided the area into 3 zones. One zone was left untouched. A second zone used only human-designed interventions, including dew traps and planted seeds. The third zone combined those same interventions with bees. Within months, the differences became impossible to ignore. The bees were doing more than pollinating flowers. Their underground tunnels acted as passive moisture channels, guiding dew below the hottest surface layers. The structure of their burrows compacted surrounding soil, reducing evaporation. Organic material accumulated around nest sites, creating nutrient-rich micropockets. These pockets retained moisture for days instead of minutes, long enough for microbial life to establish itself. Measured soil moisture in bee-supported zones increased by roughly 35% compared to areas without bees. Microbial populations surged. Beneficial fungi formed symbiotic relationships with young acacia roots, improving nutrient uptake and drought tolerance. When flowering season arrived, more than 60% of acacia flowers in bee zones produced viable seeds. In untreated areas, seed formation nearly failed. The contrast was stark and measurable. This was the turning point. Not because the desert was conquered, but because it began working differently from within. What followed over the next year was not dramatic in appearance, but it was decisive in outcome. The desert did not suddenly turn green. There were no sweeping aerial shots of forests replacing sand. Instead, change appeared in patterns that only careful observation could catch. Seedlings that would normally wither after a few weeks stayed alive through the hottest months. Soil crust softened instead of cracking apart. Shade lingered longer beneath acacia canopies. The system was no longer fighting entropy alone. One of the clearest indicators came from temperature data. Ground-level sensors showed that areas with sustained acacia regeneration experienced slightly lower daytime surface temperatures and noticeably slower nighttime heat loss. That small thermal moderation mattered. Cooler soil reduced evaporation. Reduced evaporation preserved moisture. Preserved moisture allowed microbial life to remain active longer between dew cycles. Each change reinforced the next, forming a feedback loop that required no electricity, no pumps, and no maintenance contracts. As vegetation stabilized, animals returned cautiously at first, then consistently. Dorcas gazelles were among the earliest visitors. Drawn by reliable acacia pods and shade, they began moving through areas they had abandoned years earlier. This mattered for reasons beyond presence alone. As the gazelles fed, seeds passed through their digestive systems and were deposited across wider areas. Unlike human planting efforts, this distribution followed natural movement paths. Seeds landed where conditions were already marginally favorable, not where planters assumed they should grow. Bird species followed similar patterns. Insect populations increased beneath expanding vegetation, attracting small birds. Their droppings added nutrients to the soil, accelerating organic buildup. Predators followed prey. Slowly, a layered food web reassembled itself. No single intervention caused this cascade. It emerged because the underlying biological connections had been restored. Crucially, the bee population itself stabilized. Early mortality had been high, but surviving individuals reproduced successfully. New generations emerged adapted to the exact micro-conditions of their nesting zones. At this stage, researchers began stepping back deliberately. Monitoring continued, but active intervention was reduced. The test was no longer whether humans could help the system grow, but whether the system could sustain itself without them. It did. By the second flowering cycle, acacia regeneration rates remained high even with minimal human presence. Bee nesting density increased naturally. Soil moisture retention remained elevated. The system had crossed a threshold. It no longer depended on artificial support. That moment mattered more than any single metric. It marked the transition from managed survival to ecological resilience. The researchers involved were careful not to oversell the outcome. This was not a universal blueprint for desert restoration. It worked because the bees were native, the acacia trees still existed as biological anchors, and the desert had not crossed a point of irreversible collapse. In areas where topsoil has been completely removed, seed banks destroyed, or chemical contamination altered soil chemistry, such recovery may not be possible. Context determines outcomes. Ecology is not modular. That restraint is part of what gives the story its credibility. It does not promise easy solutions. Instead, it exposes a pattern that engineers, planners, and policymakers often overlook. Ecosystems do not respond well to domination. They respond to alignment. When internal processes are restored, systems often rebuild themselves faster and more efficiently than external control ever could. To underline that point, the story draws a parallel with another quiet ecosystem engineer found far from the desert. The beaver. Like the desert bee, the beaver reshapes landscapes not through force or planning, but through instinct. When beavers build dams, they slow water flow, reduce erosion, recharge groundwater, and create wetlands. These wetlands reduce wildfire risk, improve water quality, and support biodiversity. None of this is intentional on the beaver's part. It is simply behavior refined by evolution. In parts of Europe and North America, beavers were hunted to near extinction. Rivers were straightened, wetlands drained, and floodplains engineered into submission. The result was faster runoff, drier soils, and more destructive floods. When beavers were reintroduced decades later, entire watersheds began recovering. Water tables rose, streams stabilized, vegetation returned. In many cases, beavers achieved in years what human infrastructure projects had failed to accomplish over decades, and at a fraction of the cost. The comparison is not symbolic. It highlights a structural truth. Certain organisms act as keystones. Their presence disproportionately shapes entire systems. Remove them, and ecosystems unravel. Restore them, and complexity rebuilds itself. The Negev project reinforces this principle with uncomfortable clarity. For all the sophistication of desalination plants and irrigation networks, none of them created a self-regulating desert ecosystem. They maintained green zones, but they did not generate resilience. The bees did not replace technology. They completed it. They filled a biological gap that machines could not address. This reframing matters far beyond the Negev. Across the world, large-scale environmental projects struggle not because of insufficient funding or technical expertise, but because they focus on outputs instead of processes. Trees are planted without pollinators. Rivers are redirected without floodplain organisms. Soil is irrigated without microbial communities. The results look promising at first, then collapse quietly when support is withdrawn. From an engineering perspective, the lesson is not to abandon technology, but to change how it is applied. Systems that rely entirely on external control are brittle. Systems that incorporate internal biological feedback loops are robust. In technical terms, the difference is between open-loop and closed-loop design. Nature has been building closed-loop systems for billions of years. Ignoring that is not progress. It is inefficiency. The Negev did not become green because humans tried harder. It stabilized because humans intervened less, but more precisely. They stopped trying to overpower the desert and instead restored the missing links that allowed the desert to function on its own terms. That shift in mindset is subtle, but it is foundational. There's also a deeper implication that makes this story uncomfortable for modern development models. Small, unglamorous organisms often matter more than large, visible interventions. A solitary bee can unlock changes that no pipeline can sustain alone. This runs counter to political incentives, funding structures, and public expectations. Bees do not make for impressive press conferences, but they make for durable outcomes. The final phase of the project focused on monitoring long-term stability. Researchers tracked vegetation persistence across multiple dry seasons. They observed whether acacia seedlings survived beyond initial growth spurts. They measured whether bee populations fluctuated or remained steady. The results were consistent. Variability existed, as it always does in natural systems, but collapse did not occur. The feedback loops held. What makes this outcome powerful is not its scale, but its mechanism. The desert did not need to be transformed. It needed to be reconnected. Once the right relationships were restored, complexity emerged naturally. Life did not arrive as an invasion. It reasserted itself. That distinction matters for how we think about restoration globally. Many landscapes are not empty. They are incomplete. The components remain, but the links between them have been broken. Restoration, in those cases, is less about addition and more about repair. The Negev was not rescued by spectacle. It endured because it still had the capacity to respond once the right biological trigger was restored. That trigger was small, local, and easy to overlook. Yet its effects were systemic. In the end, this story does not argue against human ingenuity. It refines it. The most effective interventions are often those that amplify what already works instead of replacing it. When humans learn to work with the smallest engineers of the natural world, ecosystems do not need constant supervision. They rebuild themselves. That may be the most important lesson of all. Not that deserts can be conquered, but that they can recover when given the chance. Not through force, not through endless inputs, but through restoring the quiet relationships that once held everything together.